So welcome to this last session for the morning. I'm David Almas from the LTDS in Lyon. So the first talk will be given by Emile Hohnadel, coming from Grenoble. He has a lot of nice videos, so we hope they will be working. So the floor is yours.
Thank you for the introduction. And yes, so do I hope as well the video will be working. I'm currently a postdoc, but I will present some of the results I obtained during my thesis, supervised by Florence Berthaille-Descoubes and Thibaut Métivé. And I also worked with Octave Crespel, who was an engineer in the team at the time I did my PhD. So like the title suggests, I have been working on the assembly of fiber with contact, and more precisely on the role of contact detection in the resulting forces in the simulation. For example, if we consider, and now it's no longer working, next. One click to play, second click to play. We can see a single hair being combed using the super helix model, which is a curvature-based model, meaning that each discretized element of the rod has uniform curvature. This is interesting because the elastic energy is quadratic in the curvature, and so it makes for a nice, simple, implicit model. And we solve the contact using the Sobogus solver developed by Gilles Davier, which is a hybrid Gauss-Seidel method. And so we obtain very nice video, but then if we focus on the forces instead of the hair on the comb, we obtain noise, which seems to strangely increase as we enter the curlier part of the hair. And so we try to first explain where this comes from, and how can we mitigate this, or even completely remove these effects. Spoiler alert, it was in the title already. This is due to the contact detection scheme used. But first, maybe if we want to focus a bit more on why the jumps increase as we increase the curvatures, we have considered a simpler test, and again, the video is not automatically playing, the curved three-point bending experiment. You probably all know the three-point bending experiment. We simply added natural curvature to the rod in this experiment. Why is it interesting? Because at the obstacle here, there is neglecting the effect of gravity. There is no external forces on this part, and so the curvature at the contact is exactly the natural curvature of the rod, meaning we can quantify exactly the effect of contact depending on the natural curvatures. And so we obtain different force displacement curve. There is semi-analytic formulation for them. And so if we compare them with the simulation this time, you cannot see it because it's a bit too light, but if we plot instead the derivative, then we can see clearly the jumps occurring regularly and increasing also for higher natural curvatures. And so what's interesting with that is that we can measure the average amplitude of the jumps as a function of the natural curvatures and obtain a nice linear relation between the two. And as I just explained, we have shown that these jumps in contact are due to the contact detection methods. Sorry, I'm losing my words. And so we can consider a very simple experiment to see this in more practice. We consider a black curve, a point obstacle P in orange. In pink, we have the exact closest point, and in blue, the approximation using the segments. And we see the two do not match. But if we increase the number of segments, we expect them to get closer together, as we can see here on the video. But this does not remove the jumps. Instead, it increases the number of jumps, actually. The problems come when we pass through the junction between two elements. Naturally, when the point P is inside the normal cone between the two segments, we see some artificial sticking effect, and this is the source of the jumps. And unfortunately, we cannot remove them by simply increasing the number of elements. As we need to change a certain number of angles, it will, increasing the number of segments, reduce the aperture of each cone, but increase their numbers. So the solution to solving our problem is high-order contact detection method, which was not classic approach in computer graphics up to now. Now it's getting more and more there, as you have seen already this morning, already with a nice keynote. And so here we can see on the zoom there is still the sticking effects. Okay. So high contact detection method, it's a domain that is more and more famous and work in different domains. On the topics of geometry, there is Lakshmanan and colleagues that presented a nice algorithm to find the closest point between 2D curves. In the domain of mechanics, Christoph Meyer has presented a nice algorithm between grid shells, or Faccio and colleagues between Rowan patterns. And even in computer graphics, actually, at the time of my thesis in 2023, a paper already had been published about continuous contact detection between high order volume. So finding the exact moment and position of impact between two volumes represented with a spline. But since we focus only on rods and we know some information about their curvature being uniform per elements, we wanted to develop a nicer and more efficient method dedicated to our rod model. And for that, the algorithm was actually developed by Octave Crespel, and it used a branch and bound method. So given two curves A and B, we approximate them using a bounding volume. If the bounding volume do intersect, then we need to branch, meaning we split our problem into two sub-problems by slicing one of the rod into two, and then we repeat. We approximate the rod with a bounding volume. If they do not intersect, then we know there won't be any contact, we can stop. If they do intersect, we repeat again and again until either there is no contact or the size of the rod is smaller than a given threshold and we have reached contact. This is a classic approach. What was interesting with this method is the bounding volume used in the approximation step. We use the Taylor-Lagrange inequality, which has a nice property of requiring a second-order derivative. But on the other hand, its volume decreases quadratically with the length of the element, meaning the volume decreases very fast as we increase the number of steps. And so we converge very quickly to a solution. In practice, if we compare our high-order model, or new model with a branch and bound model with a naive segment discretization with a bounding volume hierarchy, we obtain completely different scaling in computation time. To be honest, with the segment approach, to reach the given precision, we had to cut the rod into segments smaller than the given precision. That's why it scales so bad with the number of elements. And so we can see that if we apply this new method to the initial example, visually there is no differences to before. But this time, if we plot the forces, we have removed all the jumps. This is all great and good news. But maybe you can say we still see impact at the beginning, while there is impact when the hair fall on the comb, or at the end when the hair slip out of the comb. But what's more interesting, what's maybe more questionable is, has this even an effect when we consider large-scale simulation? Do these small jumps have an effect or cancel out when we consider, for example, thousands of hairs? And so we did the experiment. Because this was published in computer graphics, we naturally extended to other kind of curliness, going from straight hair to really curly hairs. But the other parameters are the same. We just increase the number of hair inside the wisp. And so if we focus on the middle one, which is the same natural curvature as the one we did the presentation up to now, we can plot the forces on the comb again as a function of the time. And if we compare the forces using the naive segment approach and our exact branch and bound approach, we see a clear difference between the two forces, meaning the segment approach, the small noise sums up and creates a significant shift over times. So naturally, now that what we want to do is say, how can we compare that to real experiment? Are the new forces coherent with real experiments or not? Unfortunately, this is still a work in progress that I am actually working on during my PhD, but I can show you a simpler example in two dimensions where we did quantitative comparison with experiments. And for that, I need to present another project that I did in collaboration with Tomohiko Sano from the Sigma Lab in Japan, where we considered small open rings like this, which are characterized by the opening angle phi. And he puts many of them inside a box, and a 2D box, so and compress them to see how the heats react. If I play the video, we can see some interesting effects of compression, rearrangements, and maybe more surprising, some snap fit event, meaning that one ring can snap into another as we compress them. We see some of them here. And then when we reach a critical load, we start unloading again. And we can measure again a force displacement curve. And the one he obtained experimentally looks something like this. So we have an hysteresis curve, meaning we have dissipated energy. But what's more interesting maybe is the sudden jumps that occur regularly that are due to the snap fit effects. As we can see here, when the load is high enough, so multiple rings can snap into one another, reducing suddenly the overall forces. And so to reproduce this experiment in simulation, we first needed to measure the different parameters, physical parameters in the experiment, in particular the friction coefficient. To measure the friction coefficient, we introduced a simple experiment where we only consider two rings that we snap over one another. It's a generalization of an article by Yoshida and Wada, where they considered a rigid cylinder on the lower half instead of an open ring again. And as in that article, we see only two regimes, depending only on the friction coefficient and opening angle, either what I call type 1, where we slide continuously, if the video want to play, or type 2, where we sticks. And this video does not want to play. You'll have to trust me, it sticks, and then it starts to coil, and it snaps suddenly with a quite loud noise, actually. And so what's interesting with that is we have a nice curve domain between the two, which is monogeneous with respect to the parameters. And so if experimentally we have that for one angle, we are in the type 1 regime, and another angle we know we are in the type 2 regime, then we can deduce a window of value for the friction coefficient. In particular, we use the value 0.35, and we can see that it matches very, very well the experimental result in red here compared to the blue simulation. So now we have our friction parameters. The other parameters like Young modulus can be computed easily using cantilever test or things like that. And so we can start running simulations, sorry. So again, we create an initial random configuration. Then we put the load and start loading and unloading. The colored one will be the ones that snap all together at the same time if you want to focus on them. And so then we reach a critical load, and we can start unloading again. Unfortunately, I cannot move. If I move to the next one, we won't see the rest of the video. But to move on, we obtain again the force displacement curve using the equivalent 2D rod model and high-order contact detection method. And we see similar effect of sudden jumps when snap fit events occurs. And so to compare the simulation and experiment, instead of trying to focus on the same initial random configuration, what we want to do is study the effect of the initial random configuration, see if we can find some values that are independent of them. And for that, we focus on two parameters, the maximal displacement at which we reach the critical load, and the dissipated energy, normalized dissipated energy. And so we can run many simulations, many experiments. Maybe I can start playing a bit just to show you. And we can see that for open rings, it goes very fast. For the middle, it compresses really much and snap fit events occur. But when the open ring is too big, the angle is too big, there is not enough forces and room for the type 2 snap fit or event to occur. And so there is only rearrangement of the overall simulation and no snap fit event that can occur. And so we can compute the forces and the maximal displacement for all of them. And we can compare the experimental simulation result in blue and the simulation statistic made over 100 simulations and see an excellent match between the two. Meaning we have an interesting 2D experiment with random initial condition from which we could measure significant value using simulation. If I have some time, maybe I can quickly describe a bit. The 5-star angle here corresponds to the switching angle between the type 1 and type 2 regime. And so we see that for small enough angle, we have an increase in the maximal displacement as the angle increases. And then it's decreased a bit, or maybe it stays constant, I'm not really sure. But what's most surprising, maybe, is that the dissipated energy seems to be mostly independent of the initial ring, of the initial open ring size and initial configuration. So this was a nice result. And I'm not going into the details now, but in our paper, then we extend the simulation by also varying the initial friction coefficient. But this is all I wanted to discuss about this now. Maybe just to give a quick update on the latest code I've been developing about a 2D model. I've improved the 2D rod model, mostly for computer graphics, but still we have validated it physically against, and we can do funny real-time experiments. It's mostly interactively on the computer. It's a simple, it's the same projective Gauss-Seidel method to solve the contacts and first-order semi-implicit time integration, but it works quite well in practice. And if you want to play with this model as well, there is a code that has been recently released. It's still a work in progress, but if you want to test it, it is available. And just to recap what I have presented during this simulation, during this presentation, it's that when considering assemblies of fibers with frictional contact, the contact detection step is really an important one, because using a naive low-order method can cause artificial jumps, but it is easy to find a high-order solution in general, and it can be enough to produce significant statistic on a real-life experiment from random initial consideration. Thank you for your time. And the bibliologist case.
Julien?
So you found that you have similar statistical behavior between simulations?
Yes.
Have you tried to do at least one case where you really start the same initial condition and in the experiment and you see the same jumps and the same moments?
Not on this 2D experiment, because we did not have the tool to exactly extract the initial geometry, which was quite hard. But actually, a new PhD student in the team is working now on tomography reconstruction of hair wisp to do the same experiment directly on the complete hair wisp. But it's still a work in progress, so I cannot show anything yet, unfortunately. But it's the objective in the long term, yes.
Other question? Maybe I have on your fiber reorganization, there is a time scale for the recovery at the end. Everything is elastic in your...
Yes, it's purely elastic.
What is the time scale?
Actually, these parameters were used mostly for graphics integration, so the dissipative parameter it's overlumped, clearly, and I don't know the correct, I did not use the correct time scale here. That's why it looks a bit slow to reach equilibrium. But it works as well. The 2D experiment at least use real time scale, and it works well, so I'm not too afraid about that.
Okay. So that's fine.
Thank you.
The next speaker is Alessandro. We speak about the advanced contact method for planar mechanics.
Thank you for the presentation. I'm going to present this work. My co-authors are Pietro Davide Maddio and Professor Rosario Sinatra. And we start on the importance of contact for mechanisms. If you observe these two simulations, we can observe the first simulation is with clearance in joint of 0. And the other configuration is with no clearance, so ideal joints. But in the real life, joints have clearance. So, and the ideal joint doesn't exist because every mechanical joint is given by the contact of two profiles, two conjugate profiles. So you can observe that even if they start with the same initial configuration, what happens during the simulations of these 6-bar mechanisms is that the ending configuration and changes. So the kinematics changes, so the forces changes. And another important aspect is that the deformations make the mechanism over-constrained because there is no space to move. So if you don't consider clearance and impacts, probably your mechanism will lock. These two simulations have been performed using no-smooth dynamic methods, so different from the methods I'm going to present today. So some application where we can observe contact in power transmission systems. So gears, belts are based on contacts of profile to transmit power. But sometimes we are interested more interested in transmitting motion or converting motion. So we have motion converters from translational to rotational motion or from rotational motion to translational motion, or some other mechanisms are intermittent motion generators, like the example of the Geneva mechanism that I'm going to present at the end of the presentation. Or other mechanisms are based essentially on friction, so they work thanks to the contacts and thanks to the friction. Some outlines of the method. The first phase of the method is a broad contact phase in which we find the overlapping areas between the two profiles. And there is only one restriction, is that at least 1 point for each body must be inside the overlapping area. Otherwise, we cannot satisfy the linear momentum equilibrium because we have to distribute the forces. So in cases we have only one node belonging to one body and 0 nodes belonging to the other body, we cannot satisfy the equilibrium. After this part, we are able to calculate the area using a simple Gauss formula to calculate the area by means of the coordinates of the points of the overlapping area. And in this process, we also include the intersection points. So the intersection points are not points of the perimeter, but are other points that we add to our system in order to more precisely calculate the overlapping area. And after that, we calculate the centroid coordinates. So the centroid coordinates, for example, in this case, is this point. And the formula to calculate the absolute value of the contact force is a penalty formula. So we have a penalty coefficient that multiply this area. What about the direction? The direction is more complicated because in that case, we have to, for each point of the first body that I call slave, but is symmetrical, so we can switch the bodies. And so this is the slave, the red one is the slave, and this is the master. And for each point, we define a force as the product of a pressure, Pi, and a tributary area that in this case, in planar system is only a mean length, and mean length means that we have to consider the previous points. So the points be Si minus 1 and Si plus 1. We calculate these two lengths, and we calculate the tributary area. And then the nodal pressure is given by coefficient that is a scale. So alpha S is something that scale the shape of the pressure distribution. And the pressure is also proportional to this distance that is found by means simple geometric scalar product. And this distance is powered by Q, where Q, we discovered that Q must be 2 in order to satisfy Hertzian contact. But we discovered also that Q can assume other values in order to, for example, to adapt the method to non-conformal profiles. And so in the case I'm going to present is only considering this Q equal to 2. Okay, so Q dominates the shape of the distribution, whilst alpha is the scale. So with Q, we change the shape, and with alpha, we change the scale of this distribution. So what happens after this? We can calculate the direction for each body, so for the slave, for the master, as we have to sum all the contributes for each point, and we have to normalize. But if you perform this operation, what you obtain that Fs is different from Fm, slightly different. So we finally use the difference of these two global forces and normalize to obtain the final direction for the contact. And this final direction, we use this final direction multiplied by the module K multiplied by A, that is the module that I told you before. So this is Fs and Fm that now are equal because they are opposite each other. What remains? So what we saw before can be applied for rigid bodies, because we don't need to distribute these forces on the nodes of the profile. But if we are interested in modeling flexible bodies, we have to perform an inverse process, because usually, for example, if you use the STS, you start from the element, and then you assemble each element, gives a contribute to the global force. In this case, we started from the global force. So we want to decompose the global force into the nodal contributes. So it's an opposite point of view. So what happens? We have to satisfy the equilibrium. So this is the equilibrium, the sum of all contributes, the sum of all nodal forces. Where is, okay. The sum of these nodal forces must be equal to the global one. So if you substitute, you have the first equation. And also, this is the equation for the moment equilibrium with respect to the centroid. So the moment is evaluated with respect to this point. So what you obtain is this simple system. And alpha, where alpha is the scale that I told you before, can be easily calculated. After we obtain the contact forces, now we insert these generalized contributes inside our method. And in this case, we use the floating frame of reference formulation. Floating frame of reference formulation is largely used in multi-body dynamics, but also in common software like Adam software from MSc. And it decomposes the motion in gross motion and the local deformation. What is the gross motion? So you have the gross motion, you have a point of your body. So you consider the displacement and the rotation of this frame with respect to the inertial one. And after you have that the position of one point of this body is given by the position of the floating frame plus the matrix, the rotation matrix, multiplied by a local vector. This local vector is decomposed in two parts. The first part is the initial configuration, and the other part is the local deformation coordinates that we are using. What happens? In general, these two motions, so the gross motions and the elastic motions, are not decoupled. So, but it depends on the choice that you make when you define your floating frame. Floating means that this is the body, this is the frame, so the body can move, the frame can oscillate with respect to the body. Only in the case in which you choose, for example, a fixed condition for the floating frame becomes a fixed frame. So only in that case, you have that the gross motion becomes the rigid body motion, but in general it's not. So it depends on this matrix, very important matrix, that is called the reference condition matrix, in which you impose this reference condition. So the reference conditions are linear constraints that define the nature of the floating frame. Okay, then we insert the contact contribute inside our DA system, and this is a constrained system in which this part, capital Phi, is the array of constraints in which we include joint constraints, rheonomic constraints, and we use an implicit integrator, the generalized alpha integrator. So what happens? We have to prepare for each component. We have to discretize. We have to find all the invariants in order to find the mass matrix, the stiffness matrix. And after that, we also reuse the system because using the floating frame of reference, we have small deformations. And when you use small deformation, you can provide the reduction by using, for example, is just one solution, but you can also choose different modes. I only selected normal modes in this case, but you can choose also static modes or other types of modes. So after that, you assemble your system, including all joints, and you compute the contact model, and you give the forces and torques. So this is what happens in one iteration of my system. So starting from the first example is a cam follower mechanism. So this body can rotate around this point, and in this point you have a revolve joint. Revolve joint that is connected to the rest of this circle by means RBI free elements. So RBI free elements is an interpolant element. It's not rigid. And the contact is the contact of this cam with this profile, cylindrical profile, and this profile can only translate along the y direction and is connected to the frame by means of stiffness and a damper. So what happens during the simulation? In this part, you can see the distributions of forces in one frame of our simulation. If you go to the next, this Geneva mechanism, the Geneva mechanism is we are in Switzerland, is the basis for clocks. Okay, because what happens? These systems rotates continuously, and the other system, when it engages, the pin engages inside. So you have, in this case, you have 6. So you have that for each rotation, you have a rotation of the other body of 60 degrees. Okay, so you can, you know that when you observe inside a mechanical clocks, you have the system. This is the Geneva mechanism, and this is what happens to the contact force. So you have part of the, most of the time is 0 because they are not engaged, and then you have a peak value. This is the simulation that my colleagues showed you yesterday, and is a gearbox, ordinary gearbox, and you can observe what happens in the flank of two teeth in contact. And finally, the last one is a cycloidal reducer. What is a cycloidal reducer? It's quite strange because you have an eccentric shaft, this one, the green one, that engaged by means of a revolve joint with the lobed profile, the blue one, and the profiles are cycloidal, this one. And what happens? He jumps, and when he goes in contact with these black pins, he makes a revolution, and inside this you have the output shaft. The output shaft is the red one. So it's quite strange. But what is the particularity of these mechanisms? That the transmission ratio means the connection between the rotation of the input and the rotation of the output. So the rotation of the input is the green, with the rotation of the output is the red, is given by this formula, where zeta is the number of pins and zeta lobes is the number of lobes. But usually the number of pins is 1 more the number of lobes, so the denominator is 1. It means the transmission ratio is very high. So sometimes you have 100 pins, so the transmission ratio is 100. And 100 means that when you have 100 rotation of the input shaft, you have just 1 rotation. But conversely, you have that the torque is very high. That's why this is very compact, and they are used in robotics. So we conclude the simulation. We compared with a rigid body simulation, so without flexibility. And this is what we attained. The particularity is that all contact points converges in absence of friction. They converges in this point, you can see. And you find also the torques for the input and the output shaft. And I conclude with the future developments. We want to extend to large deformations. We already have the Tangen stiffness matrix of the contact. So we obtained the Tangen stiffness matrix, but we have to change from the floating frame of reference to another method, is the absolute nodal coordinate formulation. The absolute nodal coordinate formulation is able to work with large deformation and large displacement at the same time. Thank you.
Thanks for the interesting talk. You mentioned model reduction. I wonder how many nodes you need for faithful representation, because contact is a very local phenomenon.
Yes, you're right. That's why if you if the number of reduction modes is not adequate to the case, you have that the impact only excites the first, the second, the third. So you have a global motion, but it's no more local. That's why for each case we made a like sensitivity analysis in order to find the right number. In this case, for example, I remember for the CAM one, in order to capture the local deformation at this point, we use the first 20 natural modes. If you increase, like going from 20 to 50, results doesn't change anymore. But this it changes from case to case, so you have to check. Thanks.
Question? I have a very nice one. So your systems, curvature radius are quite large.
if I add some roughness, will the method still work?
This method is curvature independent, no? Because it only works on the overlapping area. So if you have, for example, not only this case in which you have convex-convex, but you can also have concave-convex or concave-concave. But also in this case, for example, if you observe this one, we have some particular case in which the tip of this body enters. So you have a very, very bad contact because it's a point of discontinuity. But it works. Yeah, it's still working because it works on the overlapping area. Welcome. Thanks.
Next speaker is Ayman Khaddari. So we will speak about influence of numerical shape on dynamics of contact between viscoelastic beams and rigid beams.
Thank you for the introduction. So I want to share with you my advances in the thesis that I'm making about numerics of viscoelastic beams specifically. This subject is in the context of nuclear industry. Like in many compartments, we have thin model structures that can be solicited through vibrations and can hit obstacles that are considered rigid. And here are some examples of it. And the idea is to study some dynamical phenomena about like non-repeatabilities when we impose for example, a periodic solicitation, and we want also to sort which phenomena are numerical and which phenomena are physical. So we have to choose carefully our modelization. So we begin with the state of art about elastodynamic Euler-Bernoulli beam. That's the model that's the initial model that I started with. So it's a classical equation defined by initial conditions, boundary conditions, and a new contact force term defined by seniority conditions by these inequality relations. The existence solution is proven by Cutler and Shiller in 2001, and the uniqueness remains an open problem. As for the weak form, so generally we can use distribution theory and to transform the Schwarz written formulation into to this inequality, and through it we can define the domains which both displacement and velocity exist. And this formulation also helps us to define a discretization that's and due to the high order of the space derivatives, we define degrees of freedom that are displacements and rotations at each node, and we get the following variational inequalities with the matrices, the mass matrices and stiffness matrices. And if we use a classical discretization, what we have defined is a measure differential inclusion, with when we have a regular mass matrix method. And that problem, that model has been proven to have unphysical oscillations that appear and a non-unique solution mathematically. So the problem is ill-posed and a non-consistent energy balance that arises from it. So one method that I explored is the singular mass matrix method that defines two different projection spaces and define through it a velocity conversion, and thus we define a new mass matrix, but defined with these kind of projections, and the theorem like of Yves Renard proves the existence and uniqueness and the conservation of energy. So we have a solution that is that fits with our physical intuitions about elastic contacts and so on. And for the totally discretized method, we use a Newmark scheme. Although it might sound surprising, but due to the singular mass matrix method, the problem is the discretization is accurate because the terms that remain are differentiable enough. So, and we will use that scheme to look at the energy balance. So for the problem definitions, we have these constants, and we define initial conditions and two boundaries, upper and lower, and we don't have any solicitation. So we have some animations of some simulations, and here's our energy formulation that we will plot. So in here, that's a state-of-art result, a comparison between singular mass matrix and the regular mass matrix. For when we converge the time step, we get the accurate theoretical result, which is a constant energy balance and no dissipation related to contact, as opposed to the regular mass matrix where we don't have a clear pattern that converges. Now we add viscosity, and we go to the continuous model. So now we have two terms, and these are used in the industry called the Rayleigh viscosity. About the physical accuracy, it's open to discussion, but that's the model we are trying to do. And of course, since we have dissipation, we can allow a solicitation of the bases as soon as we do one, simulating friction, and we have the same scenario conditions. So also as a result, for an obstacle that is punctual, we can prove it has been proven that the solution exists, and that the solution exists through defining a penalty force and converging the coefficient to 0 to reach perfect complementarity conditions. And one of the results worked on is to extend the model for extended obstacles. So it's a different, slightly different formulation, but and I highly relied on the previous proof. Another interesting result is the existence of a solution that is energy conservative, and that is through using a regularized penalty and conversion. So the idea is to capture different regularities of terms that at the limit are ill-defined, like they are measures or distributions. They cannot are not very nice functions to estimate. And so one idea is to separate a region that never enters impact, so we can define, we can bound some high derivatives in the boundary. Like in here, we have the force, like 3 derivatives that is bounded by gamma 0, gamma 1. And we have three lemmas that's bound different terms. One comes from the energy balance, the second from the effort screw invariant, and the third is a regularity result of the gap. And we find that the energy, the dissipation related to contact goes to 0 as epsilon goes to 0. And it would, although like if it's the lacking result is of course a uniqueness result, but I think it's a good enough base to justify some numerical results that I will show later. The same thing for the variational formulation. When we use the finite element method and define in the same way singular mass matrix, and that's a theorem that we've worked on. It's to extend the well-posedness result, and thus we have existence, uniqueness, and a functional that is constant when we have no solicitation. That doesn't like. It means that the dissipation is purely viscous, and that is the extended like Newmark de Montpauli scheme that will be used. So here are the discrete energy forms: the total viscoelastic energy and the partial elastic energy W. And we start with a kinematic viscous damping, that is only proportional to the mass. And we see that for the singular mass matrix, we have a smooth function at the limit that has an exponential like shape. And we can clearly discern the two energy balances. As for the singular mass, the regular mass matrix, we see also a convergence to a constant function, but in a very slow way. And if we try the Kelvin-Voigt viscous damping, it's a different. It's a different result since we involve the higher space derivatives for viscosity, and we have pretty much similar results, except for like 10 to the power of -7, where we see the clear convergence to the theoretical result in the singular mass matrix, but also an almost constant function for the regular one, and that's probably validates that at the same time the theoretical results of the continuum problem, and the fact that the numerical scheme is made for like smoother functions, and it captures that kind of solution for that kind of Kelvin-Voigt damping. Now I go to the study of bifurcation. So as a definition, it's a qualitative change in the structure of a dynamical system provoked by a small modification of a problem of a parameter. So we have in a classical sense a differential equation that depends on a parameter lambda, and normally when we change this parameter, we can build a homeomorphism between the two flows of the solutions. But at the bifurcation point, there is a non-existent. So it's a negative definition rather than a positive one. As for the numerical methods, it's a heuristic method that uses transient regimes and from an initial conditions, and then we characterize an established regime, and from it we extract our information. That's shown in blue, and then we change our parameter incrementally. We have two. We're going to plot two. We did plot two outputs. One is the Lyapunov exponent, and it shows how a variation or our perturbation in our flow grows or evolves. So it's defined by lambda. If lambda is negative, then the perturbation goes to 0, meaning the solution is stable. If not, then the solution that we have is unstable, and that could characterize that even in the established regime we are in a chaotic solution and we are in a structure that is not punctual, and that is characterized also by Poincaré section. So we have a section, and we will study all the intersections at every period of the solicitation. And if the shape that we get has a dimension stronger than 0, then it indicates a chaotic regime. And here are our same constants, and we have a band of amplitude, and we fix our angular frequency. So now we go with our reference solution, singular mass matrix, and the parameter of the Newmark scheme beta equal 1/2 that is related to an unconditional stable solution. And we can see the connection with the Poincaré section as for the amplitude, that when we have a shape that is not punctual, it's associated to a positive Lyapunov exponent. The same for the number of elements and the time step. So we've seen that they converge dynamically in that regard. In here, we compare the penalty method to the Lagrangian method. What we see that is that the band of chaotic solutions is larger, but it has the similar shape overall, and that's the same for convergence in time steps. Before it was converged in number of elements, and in here the very interesting result is that when we push our parameter to 0, the shape of a response curve, the bifurcation diagram, converges to our reference shape of the Lagrangian method, and that means that the convergence can be characterized dynamically, except what we have the ill convergence for lower epsilons, and that's related to the numerical scheme being poorly conditioned. Okay, so now, but the problem with that method is that it's heuristic. It integrates step by step, and we would like gain some data from sensitivities from. That's where we will explore the shooting method and the continuation method. So shooting is to directly aim for the right initial condition that gives us the periodic solution, and continuation is to explore all the through the second parameter all the periodic solutions, and to trace a response curve that connects them. So, and that's the problem that we aim to study, because the tools are only defined for the smooth dynamical systems and not for a linear complementarity problem that like in the beam problem. So we start with the Duffin example, and how the equation that we try to solve with the periodicity constraint that we try to cancel, and through it we extract an augmented ordinary differential equation through the Jacobian around the initial condition. We also, so this is how we can find the solution. As for the response curve, we study we characterize the parametric equation for that for the points associated to the functional being 0. And we have a scaling equation and a pacing equation. And we extract from it a scheme, one that has two phases, the prediction phase that goes through the tangent direction, and then the correction phase that goes through the orthogonal path, doing a Newton algorithm until reaching the 0 point of h. And here is our response curve and associated to the set of equations. And as for this stability, we take the monodromy matrix and we extract and from it the spectral radius that tell us how stable the solution is. So it's similar to in the same fashion to the maximal Lyapunov exponent explored before. And we can extract like the stable branches and the unstable ones, as well as limit points that can be extracted through higher sensitivities. And now as for a non-smooth problem, this is a toy problem about friction. Okay, so this is our model. So due to the non-smooth characteristics, I took a shortcut, doing a discretization first and then a differentiation. So this is a scheme iterating of implicit Euler scheme, iterating the state vector and the sensitivity Z and on initial condition, and P also on the frequency. And we distinguish the stick and slip. So for the stick, we have a loss information, and that's it is problematic for the Newton algorithm. But overall, we have we can plot the phase portrait, and also plot the response curve associated to the problem. So that's the idea: is to go further into those methods and in parallel to explore the mathematics of viscoelastic contact problems. So that's the end.
You mentioned singular mass matrix.
Thank
I was wondering what causes singular mass matrix in this case.
It's the type of modernization. Okay, so for thin materials, what we do is discretize, is define two space of discretization for finite elements, and define velocities in a smaller one than the one we define the displacement into, and that gives us a conversion, a velocity conversion formula for with B a rectangular matrix that destroys information for U dot, and that's why we have a singular mass matrix. And
So you have velocities. The variation of those velocities will not cause any change in the kinetic energy.
yes, they don't. Yes, they don't influence the kinetic.
Last question for this morning is Lagrangian method.
Okay. Thanks for the kind introduction. Thanks to the organizers for the nice opportunity to share some experiences in over-constrained contact formulations. And we gained is together with Rolf Krause and my PhD student Felix Baumann. So the motivation for this work is biomechanics, actually osteoarthritis, a degenerative cartilage disease that is somehow clearly linked to mechanical loading of articulate cartilage. But this, the detailed mechanisms are not understood to a large extent because the stress patterns in vivo are not measurable. So you don't know what happens in the knee during loading. Cannot be measured. So one line of direction is, or research is to do an inference approach, solving an inverse problem, having skin marker measurements for gait analysis, and then couple this to a multi-body model and a articulate cartilage model for reconstructing the mechanical situation in the knee during gait and jump and whatever. So this will lead to an inverse problem with a typical Tikhonov kind of regularization for muscle force, data mismatch, multi-body dynamics of the lower limb, and quasi-static approximation of the solid mechanics in the joint, where we have, of course, contact, non-penetration here, and coupling of solid mechanics to the multi-body model. Today, let's focus on this contact problem here. As this is from a CT scan of a knee. So you have a rather complex geometry, multi-body contact, potentially self-contact, and this has to be integrated somehow into the inverse problem and coupled to the other things. So we were interested in particularly simple approach to contact problems. And what we then considered is over-constrained contact. So the contact formulation itself is quite standard. We have some bodies, here two, with a typical displacement, stored energy of volume forces, boundary forces, that's all absolutely standard. We consider frictionless contact. That may be a little bit optimistic in diseased patients, but let's go for frictionless contact now, where this global non-penetration condition that is difficult to work with. So what we do is what most others do as well, is we linearize both the energy with the quadratic energy may be regularized, where this gap function looking into normal direction from all the boundary points and have linearized non-penetration, so the motion along the normal should not be further than the current gap. So that is quite standard. Discretization is also quite standard. Of course, finite elements here yield in a quadratic discretized problem. For the contact constraints, we have this pointwise non-penetration condition everywhere on the boundary. What we can do is simply select a subset of points where to consider contact. So this then falls into the class of two pairs, node to segment or segment to segment methods. And we select just some of the constraints, typically a couple of them on each boundary face or so. We end up with a quadratic program with a standard energy and these linear constraints. So that's pretty simple. And in particular, just looking into some directions for contact is pretty easy to realize. So what are the properties of this approach? Most of you will know this. That is, it's a true outer approximation of the feasible set. So we just remove constraints from infinite many to finitely many. That means we enlarge the feasible set. Nevertheless, in particular situations, this is well known, we have exactness in 2D and for piecewise linear finite elements, these contact samples on each vertex edge incidence. Then you can recover with the discretized feasible set the exact one. So this is well known. Nice thing, it's symmetric. There's no need to look for master or slave boundaries on dynamic and changing contact. So this simplifies things. However, it's over-constrained. If you take quite a number of these potential contact samples, so far there's no structure or restriction on that. So M can be quite large. This leads to potentially non-unique multipliers and a violation of the LBB condition, which might pose some issues for an active set solver that is not aware of that situation. Okay, this is one of the possible drawbacks. If we have this setting, we can also try to mimic mortar methods simply by having a basis function and integrating both sides of the contact constraints with a quadrature formula. This is essentially just linearly combining rows of the constraint matrix and right-hand side with weights. Of course, this quadrature, the order is in general not retained unless you do something more complex, like here by Rolf and Patrick with this projection of meshes, non-matching meshes, and in a way implicitly remeshing and integrating them. So the simplest thing you can do here is piecewise constant mortar basis. I do not suggest this is the best choice, but it's one of the simplest. And we will look into that later. So let's look at some numerical examples. First thing you do is some kind of Hertzian contact on these meshes. This is just 60 vertices around the perimeter, so not particularly large. And we can look at contact pressure. This is pointwise contact pressure, and Rolf repeatedly tells me that one should not do this, but I find this quite instructive, so I nevertheless do this. So what do we see here? We have here the horizontal axis. We have the computed gap function here. Of course, here it's at 0. We have a contact area. And we recover the expected profile of the Hertzian contact pressure. Of course, this looks quite ugly, right? No one would complain against the statement. This is because this contact pressure on both sides is recovered from the piecewise constant stress in the piecewise linear finite element. And then, of course, this is piecewise constant here. So why is that looking so ugly and noisy? So one reason could be the solver, but actually, no, the algebraic error is quite small, so the residual is quite small. Solver does its job. It could be the contact discretization. So let's change this from 2 contact samples per edge to 15, and then again look at a mortar discretization with this piecewise constant mortar basis function. And we see it's about the same. Have you seen the difference? Actually, there is some, but it's difficult to spot actually, unless you switch forward and backward. So the third option, which could be the cause for ugly picture, is finite element discretization. And this is actually the case. You notice here, even outside of the contact zone, there's some contact pressure, or we reconstructed pointwisely, but this is simply due to the finite element discretization itself. Right? So this should improve if we increase the order. Let's do this. Actually, it improves quite a lot. There's still, you see the P2 finite element error here, but it's much smoother. It's also piecewise linear instead of piecewise constant. So actually the contact discretization is quite nice, but the when you plot pointwisely the reconstructed contact pressure, you actually see the finite element discretization. Another example, that hexagonal double annulus here. These are actually two different bodies with a very small gap in between on the order of 10 to the minus 4. And we rotate the inner one. And the question is, what solution do you expect? It's difficult to tell on that scale because these could be two different problems. This could be a kind of wrench where this is actually the geometry, just with a coarse grid, or it could be a very coarse discretization of something like a shaft bearing, where we expect we can rotate the inner annulus without any contact force whatsoever. So let's see if we compute both and rotate this. We see here the stored energy over the rotation angle. And of course, when we are in that configuration here, we have quite some deformation and some energy. So we have a high maximum energy. If we have a better approximation of the circular geometry with 48 vertices around the perimeter, then of course we get a 4,000 times smaller stored energy during the rotation, which is exactly what you expect from analytical considerations, very simple ones. However, this is not particularly nice, right? You would expect to have no contact force at all. You can, of course, refine, okay, and this works. So this converges to 0 nicely with the expected order of 4. But if we look at what mortar does, again, this very simple piecewise constant mortar basis, then it drops to 0 much faster. And this is nice, right? So mortar is much better in this example. Question is why? Why is this piecewise constant mortar so good? We face exactly this situation. We have two edges when we rotate that at some points and configuration are in this situation. We have a positive gap, we have a negative gap here. We integrate over and the average gap vanishes. So this is why there's virtually no contact force in the mortar discretization. And what we do is we make two errors. So one is we ignore local penetration here, and the other is we have a bad geometry representation. And it happens that these two errors cancel out. We may be happy with it, but we may also take a more dogmatic point of view and say, okay, we should do both right, because we don't want to rely on this canceling out always. So no local penetration. We stick to the very dense sampling of contact, and we take a good geometry representation, at least for computing the gap. And this can be done, of course. This is quite old, goes back 25, 30 years ago. We can interpolate smoothly with continuous normals, a piecewise, say, piecewise planar surface, as shown here as an example, where this is actually the geometry description, but what comes out as an all-weed structure. So this works nicely. And if we do this, then of course, what we expected is we observe that the contact pressure converges very quickly to very small values, essentially 0. And we do both. There's actually no penetration pointwisely at all, well, on the sampled points. Okay, I have not said anything about how to solve these systems so far. They are very, very sophisticated and highly efficient multi-level contact solvers. For example, here, this monotone contact multi-grid by Wohlmuth and Krause. This relies on a pointwise Gauss-Seidel smoother for box constraints, then convergence is guaranteed. This is very efficient. However, it's also very complex because you really have to enforce these box constraints, which means you have to separate tangential and normal displacements. You have to couple opposing faces on the contact and multi-body contact for separating joint motion from opposite motion. You need to a recursive modification of the hierarchy, and this is all quite complex to implement. And this is why we did not do this here. These requirements, in particular, are not satisfied by this over-constrained contact formulation that I presented before, so we had to do something else. Particularly here, these point smoothers, of course, make no progress in multi-body contact. Bi-orthogonality is not available here because we have these, say, there's no real connection between the contact samples along the surface and the degrees of freedom on the surface. So what we go for is we take a group of degrees of freedom, essentially those that are connected to each other by constraints, and then we take that subset and solve a local QP, a small one, right? And do a lot of them, so all over the surface, and that is a kind of block Gauss-Seidel approach that takes the QP structure into account. And of course, we can do this in a multi-level hierarchy. That is quite standard here. We so far just projected on the primal side, taking all the fine grid constraints with us. This should be improved by coarsening also the constraints, as has been done here, for example, in the group of Wall. But so far we didn't. And then we do a V-cycle that appears to work. Is nice because it has a high arithmetic density on the local solvers, these QP solvers. Unfortunately, there's no convergence proof because this does not fall into the category of block Gauss-Seidel methods with a matching box constraint structure. And as we respect here all the fine grid constraints exactly, is known that the coarse grid corrections may become ineffective. So what one can do is to relax this a little bit, go to penalty and augmented Lagrangian methods. That gives a little bit more leeway to the coarse grid corrections to actually make progress. So we have a multi-grid for the block now AL smoother. We have guaranteed linear convergence, at least for sufficiently large penalty. We have effective coarse grid corrections because we allow them to do a little bit of penetration during the solution process. We have mesh-independent convergence empirically. So this is for refinement levels 5 to 9, exactly the same slope here. But of course, we lose it a little bit. It's now infeasible. We can encounter penetration during the solution process. And it can be sensitive to the choice of the penalty factor gamma. That is well known. We can look at the contraction factor of multigrid here. So this is for a penalized point smoother, so essentially Gauss-Seidel. This is fine for a relatively small range of penalty parameters, relatively small penalty parameters, and then quickly deteriorates to quite large contraction factors. So this is then inefficient. With these penalized block QP smoothers, this is much better. We have a much larger range of penalty factors where we have a good contraction before it starts to deteriorate, of course, at some point for large penalties. is also quite robust with respect to the number of contact samples per edge, so we can be very flexible there. It doesn't really affect anything. And of course, what's usual Gauss-Seidel structure converges faster than Jacobi, and the multigrid, of course, does a decent job because without multigrid, it's essentially not converging. Okay, so far I've shown 2D examples for illustration. This is, of course, works as well for 3D problems and more complex geometries. This also works with semi-geometric multigrid if we don't have a grid hierarchy in geometries like that come from, say, CT scans. So this works as well as expected, so can be combined quite flexibly with quite a number of other approaches. So with that, I would like to conclude. So we have seen that the symmetric overconstrained contract formulation is quite simple to implement. Even I was able to do this. It's highly flexible. You can choose at will number and position of contact samples. That does not change anything. It's quite nice for multi-body and self-contact. It still yields results that are comparable so far. What we've seen to mortar discretizations works well with multi-level augmented Lagrangian methods. In particular, it's also nice to parallelize on modern CPUs, at least due to the arithmetic density of the local QP solvers. And in total, this package appears to be quite useful. Of course, there are limitations and caveats. There are so far no discretization convergence theory, and you get the usual, say, penetration with penalty and augmented Lagrangian formulations and so on. So it's not the best method for everything, far from that, but I think it's an interesting approach to study. With that, I would like to thank my colleagues Rolf Kraus and Felix Baumann, and you for your attention.
We have time for questions.
I have a couple of questions and one suggestion, or one comment. This wrenching, so it's the babushka paradox in a sense, and there are some. Okay, so if you have a circle and then you cut it in like that in finite element, so there will appear this sticky,
yeah.
And the question is that we discretize how one way is to just use curved elements for the geometry, and you probably can get around it. But the question is, if you don't do that, how does it influence the finite element method? And there are some really recent papers in that. Richard Scott has worked on it could be 2-3 years ago, and I saw a recent preprint on that, so I could.
Yeah, that would be great.
But then when you use the motoring and you use a piecewise constant and a linear,
yeah.
So I'm sorry to say, but it's not stable.
That might be.
It's mesh dependent. So when you go like this, it works, doesn't work, doesn't work. So when the meshes matches, it's not stable.
Okay.
You can fix it very easy. It takes you 10 minutes to fix it, and then that's to when you have a triangle with one edge on the boundary. On that, you increase it to a parabolic, and then you have stability, and you shouldn't have any problem with that.
Yeah. Okay. Thanks for the suggestion. What I computed here, I had shown this curve here with that was obtained with this piecewise constant mortar
unstable, I immediately believe. In that example, I did not see any instability that I would have noticed. So maybe I was lucky.
Right, no, it's like that. Believe me, I could give you that counterexample of the proofs. But anyway, okay, and then the suggestion you had two errors that cancel each other. And then you said it, which of course is got good luck. And then you said you take a more dogmatic approach.
This one, yeah.
Why don't you say a more scientific approach? To me, dogmatics sounds negative.
Yeah,
or a common sense approach.
Yeah, that is not necessarily the right way to see it, I would claim. So it's one way. So try to do both correct. And stick to.
And then do both right. I think that's not dogmatic. That's a common sense.
Yeah. That's quite possible. On the other hand, you could say, okay, local penetration, that is on the order of the mesh size. Okay, why do I care? So that's also a point of view that one can accept, right? And people do. So
No, you could say I take a numerical analysis approach. Yeah. So in numerical analysis, you make errors everywhere.
Yeah, sure.
So this error is you handle, but just it's also a scientific.
Yeah. Sure.
For me, at least, dogmatics.
Okay.
Sounds like the Pope saying that you should do this. Sorry about that.
Fine. We can discuss wording.
So in the end, are you using the hierarchical geometry or the geometry?
Yeah.
Courses,
yeah, exactly. It's just based on that paper here that describes kind of B-spline approximation when you with a more or less complex construction of normals and interpolation of normals, and then a B-spline surface on top, but that guarantees a G1 continuous surface and converges quite quickly towards smooth representations. It's not exactly here in this circular geometry. It's not exactly a circle that is recovered, but it's quite close.
One option would be just to use like Sabo and Babushka do in E-version. They use a blending function, so they get the geometry is disconnected from the Hohnadel. You get it exactly. So, or even a quadratic. I don't think you need a B-spline.
That's true for this example, but remember we are interested in biomechanical application. There don't have say exact description, right? The geometries come from voxel images of CT that are then meshed and segmented then meshed. And so we don't have the exact geometry, right? But we have piecewise planar approximation and then face these issues, and with a G1 continuous surface approximation still, we get rid of some, say, artificial friction there. I think so, yes. Yeah. Otherwise, as we can see here, you get this, sticky rotation. So you feel it need to move when you move. Yeah. True.
Okay, so let's ask Martin for the speaker.